So here's the deal. Is geometry considered a hands-on science? Is it in the same category as natural sciences? Definitely not. Don't even try to place geometry in the science club. When we talk about science, we usually think about math, physics, and chemistry, right? But hold up, that's not quite right. If you peek at university programs, you'll see subjects divided into arts and sciences, with sciences referring to natural sciences. And guess what's listed as the first subject under sciences? Yep, it's math. But seriously, how can math be lumped in with natural sciences? Math should hang out with natural sciences, forming a dynamic duo called mathematics and natural sciences. That actually makes more sense. Because, you see, math isn't your typical science. It doesn't rely on observations and experiments like the other sciences do. Geometry, in particular, isn't built on observations and experiments either. Alright, let's focus and make a clear distinction here. We need to separate things that we can know from things that we can feel, draw a solid line between them. We Chinese folks may not usually do this, but right now we're talking about Western ideas. It's important that you draw this line. Don't come at me talking about something you can feel and claim you know all about it. Nope, that won't fly. You're simply sharing something you can sense. You haven't told me about something you can truly understand yet. This line needs to be crystal clear. If you don't get this separation right, you won't grasp Western thinking. We'll dive deeper into this soon and break it down step by step. For instance, in geometry, there's this rule that says, the shortest distance between 2 points is a straight line. Everyone on board with that? No objections. Then this one student pops up and asks the teacher, "Hey, how many lines have you drawn from point A to point B, and have you actually found out that the shortest one is a straight line?" Now, this puts the geometry teacher in an awkward spot, right? But the teacher would explain to the student like this: I can draw endless lines from point A to point B, which means I'd need to measure them endlessly to finally figure out that the shortest one is, indeed, straight. Can you imagine dealing with that many lines? There's no such thing. If I just say, the shortest path from point A to point B is a straight line, you're on board. Is this something tangible? Not really. What do you call it then? A knowable thing. The stuff you can physically feel are points A, B, C, D, and as you measure them, you can keep measuring forever. That's the tangible part. However, there are some core principles that reason lays down. Once reason makes its call, that's when the knowable thing comes into play. Geometry discusses triangles. How is this discussion carried out? Is it that we discover in the real world that there are many things shaped like triangles, and then these are generalized, leading to the discussion of the properties, axioms, theorems, and corollaries of triangles? Is this how it is done? We discover various things shaped like triangles, we then generalize them, identify their common features, and then study these common features themselves. This is how we study geometry. If this is how it is studied, then we are really treating geometry as a natural science, that is, basing it on observation and experimentation. But this is not the case. In geometry we discuss triangles regardless of whether there are things shaped like triangles in the world. In reality, there are no such things in the world, yet we still discuss triangles. Once things shaped like triangles appear in the world, these things will definitely conform to all the discussions we hold about them. For instance, let's dive into the first lesson of geometry. What's on the agenda for our first class? The basics of geometry, of course. So, what are these fundamental ideas we're talking about? Well, we've got points, lines, planes, and solids. Let's kick off this discussion. So, what exactly is a point? It's like the purest form of position. We call it pure position in English, basically just a dot on the whiteboard. I point it out and then ask everyone to focus on what a point really is. It's got no length, no area, no volume. Are we on the same page? Now, how about a line? A line comes about when points decide to go on a journey together. Remember, a line is just the trail left behind by moving points, no area or volume involved, just the path of those points. Now, let's move on to the concept of a plane. A plane is what you get when lines start dancing around. Imagine starting with a straight line and then stretching it out to create a rectangle. A plane is basically a flat surface that doesn't take up any space, born from the movement of lines. And what about solids? They're the next level up, formed by the movements of planes. Picture taking that rectangle, picking an edge as the axis, and spinning it around 360 degrees to create a cylinder. Voila, there's your cylinder. When I was all fired up and talking my talk, a student raised his hand and said, "Hey, teacher, you mentioned a point has no length, no area, no volume. But seriously, if you zoom in with a microscope, where's the missing length? Where's the missing area? Where's the missing volume? It's more like a mountain." I was caught off guard and had to point at the whiteboard with my pen. It's just how it goes, we call it a diagram. But let's be real, the point I draw on that diagram ends up looking more like a mountain, right? Basically, I'm diving into those ideas that we all have inherently. Points, lines, planes, and solids are all part of our geometric toolkit. We may not talk about them when they're not at the forefront of our minds, but in a geometry class, we unpack and chat about these built-in concepts one by one. In real life, you'll never come across perfectly clean points, lines, or shapes like in geometry class. So what's the deal? It means that geometry isn't all about studying real-world stuff. If you want to dive into real-world things, that's where science comes in. In geometry, we're more into talking about those built-in ideas lingering in our minds, our natural sense of logic that quietly makes judgments without us even knowing. That's what we call geometry. When you hear this, it might mess with your common sense beliefs. So, what are these beliefs anyway? Think about it, where do you reckon balls come from? How do we even realize that there's such a thing as a ball? We might look around and see all sorts of round stuff like soccer balls, apples, pears, or just some clump of dirt that's all round. And then, after seeing all that, do we start putting it together and thinking about balls in general? This is basically the classic way of thinking in philosophy, starting with noticing individual things with our senses, then moving up to more general ideas, and eventually coming to a common understanding. We usually call this epistemology, or as it's also known, reflection theory. If we buy into the reflection theory or epistemology, it's like saying we're empty mirrors when it comes to knowing stuff. We use our senses to check out the world around us, kinda like a reflection in a mirror, and that's how we kickstart knowledge. We often think of ourselves as the brains behind knowledge, picturing ourselves as empty mirrors reflecting everything, right? Nope. For those ready to join me on this journey, we're not blank slates when it comes to knowing, we've got something going on. Knowledge is a natural way of understanding that we all have, even if we don't realize it. In reality, we use this way of knowing to make sense of things. It's more than just reflecting back what we see. Let's take a look at the example we just talked about. We set up a football, a spool of thread, some apples, and pears on the table, along with a boxy item like a pencil case. But hey, some of these things are roundish. Now, imagine we bring in a kid. Can the little one group these items by putting similar ones together? And guess what? The child nails it and groups the football, thread spool, apples, and pears together. So, how did this all happen? The child paid close attention and noticed that these objects share some common traits. But why did they catch on to these similarities? It's because deep down, in their mind, they have this pure notion of a sphere. Without that mental image of a sphere, they'd never think to group these items together. This is what we call having a pure intuition within us. And when it comes to why I see something as round, calling it a football, and another round thing, labeling it as a spool of thread, or even looking at an orange or apple as round, that's where our intuition comes into play, also known as empirical intuition. Now, when we wonder which of these two intuitions comes first and builds on the other, the usual idea is that we get pure intuition from a lot of real-life experiences. But actually, it's the other way around, because I have that gut feeling of pure intuition. That's why I sort things out based on my experiences. So, in simple terms, my pure intuition forms the foundation for my empirical intuition. Alright, let's check out these 3 statements, 3 judgments. I'll write them on the board, and we discuss about how they're connected. Everyone, take a look at these. First judgment, this is a square table. Second judgment, anything square must have 4 right angles. Third judgment, the essence of being a square is having 4 right angles. So, the first one is clearly focusing on a specific thing, a particular judgment. The second one is more broad, talking about all square things, known as a universal judgment, noting they all have 4 right angles. And now, the third one, it's all about the intrinsic nature of squares, explaining that what really makes something a square is having 4 right angles. It doesn't even touch on real-world examples, just delves into the core qualities of squares themselves. The first one talks about specific stuff, the second covers everything, and the third is all about geometry, not real-life experiences. So, how do these 3 judgments connect? Do we need the first judgment to back up the second one? We look around at individual items, like that square stool or that square box, and eventually, we end up saying all square things have 4 right angles. That's usually the way it goes. Where did that third judgment even come from? What's its deal? It goes further than the second one, getting deep into what makes squares squares. We tend to see the first judgment as the starting point for the second, and the second as the basis for the third. That's just how we usually see things. But actually, it's all flipped around. If not, geometry would rely on observations and experiments. But in reality, geometry has 0 to do with those, it's all about pure concepts. Ancient Greek philosophers once did this cool experiment with a 12-year-old slave. This kiddo couldn't read and had 0 chances for schooling. But the philosophers explained 3 geometric rules to him, and he nodded along to each one. This young lad hadn't learned anything before, yet he totally got what the philosophers were saying and could use these geometric rules like a pro. He even solved geometric problems like it was nothing. No need for fancy knowledge or experience here. So, yeah, that third judgment is just pure guesswork, plain and simple. We don't need actual square things around for this discussion. We're just talking about what makes squares tick. It's all because of that third judgment that we can group things in the world as square objects. And because of these square things, we can point to something and call it a square table. But to call it a square table, we gotta have the idea of squareness in our heads. If squareness wasn't a thing we thought about, how could we end up with a square table? So, what's up with geometry? It's all about pure reason. Why say pure? Well, it means there's no sensory stuff involved, no sensory materials. Once you strip away all the sensory elements, what you're left with is just the form, the pure form. And when you clean out all the sensory distractions and lock onto that pure form, what do you call the ability to grasp it? Reason. That's what we call pure reason. So, yeah, it's like I said before, even if there are no real circles, triangles, or cubes around, geometry can still analyze and study them. And when these shapes pop up in the real world, they'll match up with all the rules and theories that geometry has already established. That's basically what geometry is all about. Geometry really took off with Pythagoras, even though it wasn't fully figured out yet. Something big was on the horizon. Take, for instance, what we call the Gugu theorem, 3rd century BC, in China, known as the Pythagorean theorem, 6th century BC, in the West. So, how does this theorem work? It's all about the sides of a right-angled triangle. The deal is, when you square the lengths of the two shorter sides and add them up, you get the square of the longest side. In other words, a squared plus b squared equals c squared. Simple as that. If we take a right-angled triangle where both legs are 1, what's the deal? Well, c squared ends up being 2, but that's already a squared number, so what number is it really? In the equation a squared plus b squared equals c squared, with a and b as 1 each, c squared turns out to be 2. So how do we figure out exactly what c is? By taking the square root. And the answer? An infinite decimal, 1.4142. This is a big deal. So, in this triangle, we've got this side called c, and its value is like the square root of 2, which basically means it's this never-ending, infinite decimal. But is it like a real, sure number? Yup, it is for sure a proper number because the distance from here to there is fixed, it's a definite length. Even if we can't write it out as a regular number, we just slap a fancy symbol on it, the square root. This discovery in geometry has caused a stir in the world of number theory. And from all this, a whole new idea was born: irrational numbers. This is how geometry has shaken up number theory. As geometry was making its way forward, it stumbled upon the Pythagorean theorem, the one about the relationship between the sides of a right-angled triangle. And within that relationship, something cool popped up: the square root of 2. It turns out the square root of 2 is this never-ending decimal that you can't fully write down, but it does represent a real length. No matter what, you can't argue that it's a concrete number, even if it doesn't play nice with regular numbers. That's where the square root comes in, unveiling the wacky world of irrational numbers.